so let's continue. So for our second talk, we're very happy to have Neil Calkin from Clemson University. Neil was a graduate student of Ian Goulden, and he's going to talk about what Newton might have known. So take it away.
Thank you. It's a great pleasure to be back in Waterloo. It's been a long time since I was here. I'm going to talk about experimental mathematics because I don't do very much enumerative combinatorics these days. And rather than talk about something really old, I thought I'd tell you about something that is in fact really old but was new to me. And I want to talk about some pedagogy of regarding mathematics as an experimental science. This is joint work with some students. Adam Haycock is currently a graduate student here. I don't see if he's here today. To the organizers for the invitation, my co-investigators and students, and especially Ian and David. Here's to Ian and David. Oh, and of course to you, the audience. I think we all do math, right? So surely it must exist. A concept like pi and fundamental theorem of arithmetic. This is chemistry. There's a lovely quote from Calkin. I have a spare unoccupied quarter of an hour. I've often employed a or 1 to 2000 prime to how fast have those abilities. Way that they could not. They joined Devlin wrote a moderately mathematically sophisticated audience, and they give Doesn't mean they will match the graph. A favorite example of this is inequality. On the left. Then they will completely ignore it. About much more. To very good reasons for being involving the E and F third. Sufficient. Question we're investigating. In fact, an example of that would be the identities George was talking about. These things we're computing. Let's hope that improved insight gives us help to answer a question. How we should compute? We should use appropriate tools. Okay, of course. But also SageMath, Maple, Mathematica, MATLAB, C++, Python, etc. And then some other tools like Neil Sloan's fabulous online encyclopedia of integer sequences. I used to spend a lot of time looking at sequences, trying to figure out what they were. I really enjoyed it. Neil took away my job. Still see the 20 years old. It's a fabulous resource. And then the sadly defunct inverse symbolic calculator, which was a project of the Norway brothers, and appears to have gone unsupported since John said 6 years ago now. You could put in a real number, and it would tell you things about numbers close to that, and hopefully things about the number you're interested in. Whether it's e plus pi times log of 2. So, when should we compute? Well, obviously in the beginning when we're trying to figure out a reasonable conjecture to invest. In the middle, when you're trying to understand why the conjecture is reasonable, it might be true, and at the end, we're trying to prove the conjecture. And then even with LaTeX and stuff like that, also when writing up the proof. Who should compute? Everyone but Tim Gallis. Tim's a fabulous mathematician. He has a fabulous blog, and he posts questions on the blog, and people will compute for him. He describes it as a high-level programming language called blog. And he posts a question. Probabilistic processor operates, and at the end of this process, if you're lucky, your description gets translated into a language that the computer can understand, and the algorithm is implemented. The amazing thing is one is often lucky. I think by one here, he means he is often lucky. I don't know anybody else who programs in this language. He says it's related to grad students, and I actually program in undergrad as well. In fact, I teach a course pretty much every semester, intermediate math computing. So this is a math major course, teaching them how to compute so that they can go away and learn to program, which is the underlying goal of the course. I teach it as experimental mathematics. I want them to take questions, open questions, to explore, in addition to known mathematics. So I will have them look at, for example, open problems. The 3n+1 problem, Goldbach's conjecture, the Kolakowski sequence, which I discovered when I started looking at it, that Ian has one of the better papers on, I gather. If you don't know the Kolakowski sequence, it is a beautiful self-describing sequence. And it is clear that the density of 1s should be equal to the density of 2s in this sequence. It must be true. And do you still have the best bounds for that, Ian? Or has anybody improved it so far? Okay. And I have a look at whether real numbers look random, normal. And I'll have them look at things like Newton's method, continued fractions. I like to teach them some mathematics in this course that they won't see in the standard math curriculum at Clemson University. We don't have the best undergraduate curriculum there. We're not a pure math department where we teach algebraic geometry. So I like to do things like continued fractions in detail in this course and have them explore continued fractions so they can learn some mathematics while learning mathematics. Speaking of doing computations, you'll notice I've got some quotes scattered through this. I'm hoping this talk will be fun. A wealthy German merchant seeking to provide his son with a good business education consulted a learned man as to which European institution offered the best training. If you only want him to be able to cope with addition and subtraction, the expert replied, then any French or German university will do. But if you're intent on your son going on to multiplication and division, assuming that he has sufficient gifts, then you will have to send him to Italy. These days, we don't really teach long division. Very much more than a little bit in fourth grade, something like that, one of the earlier grades. I never have to do long division. When was the last time anybody did long division without using a calculator or a computer? We just don't do it. Okay, so I ask my students to recall Newton's method or the Babylonian method, Enumeration. Does anybody know of a good reference for this actually being Babylonian? The earliest known written record of it I know of was Heron's formula, Heron's method. But it's often known as the Babylonian method. And I was asked recently, oh, can you tell me why it's called the Babylonian method? I could not find a reference for it. So if anybody does know of one, please email me. So this is for finding roots of functions, approximately. The Babylonians apparently did it for the square root of 2. The basic idea, I hope you all recall, if you don't, I will remind you. You take the tangent to the curve at some point, not at the root, and you find where it intersects the x-axis, and you use that as your next approximation. And, you know, by the way, did you know before Newton invented gravity, people could fly? This picture has got so many things wrong with it, but incidentally, my thesis advisor is power 19, which I think means your thesis advisor is the 18, and your thesis advisor is the 17. I had no idea of that until my third PhD student was about to graduate. And I said to her, I'm really sorry, I don't know my lineage going back past David. And she said, oh no, math genealogy goes way further back than that. Somebody had recently put in David's advisor, and David's advisor's advisor, it goes back to me. Very proud of that. So, a picture's worth 1,000 words. Well, if a picture's worth 1,000 words, why did it take up 1,000,000 times as much memory? So we've got a point, x0, where we evaluate the function. We find the tangent line at that point. We find where the tangent line intersects the x-axis, and that's our new approximation. And we iterate that. We take point xn and find point xn plus 1 in exactly the same way. And we can write down the formula. You all know how to do this. Everybody who's taught calculus has taught this. Usually in a class that is given short shrift, but it's on the syllabus and it will be on the exam, so you have to teach it. So let's find the square root of 2. Starting at 1, we see the second integer is 1.5, the next one is 1.416 recurring, and then several more digits. In fact, at x5, we're already correct to the accuracies I'm displaying. So, convergence is fast. So I said to my students, I want you to investigate how fast the convergence is. Can you talk about the speed of convergence? I'm not really a numerical analyst, but I play one in that class that day. And they don't understand how to investigate the convergence here because it is not a very, very simple pattern, particularly if you start far away from the answer. So how can we understand it better? And so I say, compute these as rational values. Perhaps that will help. It's clear that they are rational because we have a rational function at the previous point, the derivative, and everything is rational. Can we spot a pattern? Well, the pattern is obvious. No? To a number theorist, it actually might be, but to my undergraduates, it's not. So I assign another assignment. Go away and learn about continued fractions. I'll tell you a little bit. You go away and program how to find continued fractions. Yes, I know Sage has it built in, but you write a program to do it because you will learn how to compute by doing that. And see if you can spot a pattern. Continued fraction as a phrase goes back to 1695, although in some sense the history goes back about 1500 years. And in some sense, all the way back to the 3rd century BCE with the Euclidean algorithm. So we start computing the continued fractions. The first one is 1, 1 plus 1 over 2, 1 plus 1 over 2 plus 1 over 2 plus 1 over 2. Oh, x3, I think we can begin to see a pattern. So this is part of a pattern in which I teach. Find a better way of doing something. In this case, find a better way of looking at the data so you might be able to understand it. Sometimes it might be find a better algorithm to compute something. There's a better way to compute the Fibonacci numbers than just the sum of the previous two. So the pattern is clear. X1 has 1, 1. X2 has 3 2s. Sorry, 1, 2. X2 has 3 2s. X3 has 7 2s. 15 2s. It's clear the pattern is 2 to the n minus 1. So then I say, well, this looks like a sequence that's a subsequence of a much denser sequence. Let's look at what happens if we look at all of the continued fractions that are just 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2, some number of 2s, not just 2 to the n minus 1 of them, k of them. So throw in the extra terms, find the patterns, learn about continued fractions, go away and study the recurrences involved in continued fractions, because their math is absolutely beautiful, and they're not going to see it anywhere else. And then I show them the OEIS, the Online Encyclopedia of Integer Sequences, and they look this sequence up, and out it pops. We can identify the numerator and the denominator as explicit functions of √2 and n. And then I use absolutely standard resources these days. Wikipedia is fantastically reliable for mathematics. And if it's not, I get my students to write in and rewrite it. So we find the expression for them, we use induction and the Newton's recurrence to prove that that is correct. And so the formula we get is a combinated expression involving powers of 1 plus √2 and 1 minus √2 raised to the 2 to the nth power. And I say, well, if we've got this pretty answer here, it's a bit messy, but it's not too bad. How about if we start somewhere else? I knew this going into teaching this particular project. I didn't know this. But I figured there was probably something there. So I said, let's go and find out. Start with different starting points. Try to find continued fraction patterns. Try to use denser sequences. Use the OEIS. Incidentally, if you're an OEIS user, it doesn't have all sequences in there. But sometimes if you have a particular term of a sequence, and that term is big enough, you can search on a single term and it will return 3 different things. And it may be that one of them is the thing you're looking for. And that happened in this instance. So starting, we get a formula very similar to the previous one. Oh, there's something going on here. Next assignment, try and do the same thing instead of for root 2, for root n. Arbitrary starting point, and find this beautiful formula. Starting at a over b and approximating root n, this is the nth iterate. I did not realize that for Newton's method on quadratics, you can actually write down exactly the nth iterate. So we discovered and proven a very pretty result. It was not new. It's certainly not well known. The class moved on to a new project and the work was put aside until I was working with some undergraduates. We returned to this and started looking at the original question, which is, what can we say about the error? So if we write our starting point x0 as square root of m times 1 plus epsilon, so a multiplicative error 1 plus epsilon, and look at the nth error being multiplicative error of 1 plus epsilon n, you apply Newton's method directly, you get a mess. But if we look at this formula, which the class had obtained, and we look at 1 plus epsilon n times root m, we've got a root m in front. So the messy numerator over denominator is 1 plus epsilon n. So we divide by a plus b root m and play around. And what we see is there's this remarkably nice formula for the nth error. Epsilon n is the original epsilon raised to the 2 to the n, multiplied by 2, divided by 2 plus epsilon to the 2 to the n, minus epsilon to the 2 to the n. Have any of you seen this before? I do not know why this is not an exercise in every calculus text that does both induction and Newton's method. It is already known. I eventually traced down a trail of about 8 numerical analysts, ending up an electrical engineer, retired electrical engineer at Berkeley, who had taught an equivalent formula, slightly different presentation of it. And it does appear in a couple of books, but it's certainly not well known. So this was a jumping off point. Now we can ask about what happens if we start with a different quadratic. What happens if we start with a different equation with a quadratic root? For example, x minus m over x. We'll get a different recurrence. How do the iterations behave? What happens if we start with a different conic? And what happens if we start with non-quadratics? Are there any nice patterns? I suspect that the first three questions there have nice answers. And unfortunately, my students graduated and I'm doing other things. But I don't think the non-quadratics question will likely have a good answer. So everything we've talked about so far has concerned approximating the square root of m when m is positive. The algebra, though, certainly works over the complexes. It may not work over root 2, a field of characteristic 2. But most fields, the algebra will work. In particular, we could try and find I. So explore the equation x squared plus 1 equal to 0. Now, I will point out that because we're starting with a real value, or in fact, a rational value, and we have a rational expression of that rational value for each iteration, we will remain rational. We will never get close to I. it's known that this, if you take this expression, you see chaotic behavior when iterating Newton's method on this equation. And this chaotic behavior is completely captured by the expression we have for epsilon sub n. So what do we mean by chaotic behavior? Chaotic behavior means that you may have arbitrarily close starting points that will end up not being close together after some period of time. We can know the weather very precisely today, predict it pretty well for 3 days from now, and not have a hope for predicting it a month from now. Very slightly different weather conditions could end up being very different. It's often expressed as the butterfly effect, that a butterfly flapping its wings in Africa, it's usually said, causes some weather. It's no, there will be differences in weather depending on whether or not the butterfly flapped its wings, but it's, when you say caused it, it sort of suggests a strong causal thing, and it's merely that the difference between initial conditions is slightly bigger than 0. We often think of chaotic behavior as meaning it bounces around a lot. That's not what it means. But here we do see it bounces around a lot. If we start at 1.1, the next value is 0.09, then -5, -2, -1, -0.4, then up to 10 point something, 5 point something, 2 point something, 1 point something. And these are exactly the values generated by square root of m times 1 plus epsilon sub n with the appropriate initial conditions and n. So let's see that this really is chaotic in the sense we'll look at two very close starting positions. We'll iterate starting at 2, and we'll iterate starting at 2.0001. And we see that the difference between the x0 and y0 is 0.0001. Difference between x1 and y1 is actually even smaller. x2 minus y2, still small, and it remains small, gets up to about the initial difference at x5. And then at x6, it's about the same. x7 a bit bigger, x8 a little smaller, x9 a little smaller. Seems that they seem to be staying fairly close together. But if we compute a few more iterations, it looks good until x13. Suddenly x13 explodes. They look like they're tracking each other very closely until suddenly they just blow apart. But again, these values are exactly what the epsilon n equations predict. And so my conclusion here then is that this is predictable chaos. Chaos is predictable. So my thanks for your attention, and I will stop there. I managed to get us back on track.
Okay, thanks. Are there any questions?
Well, so for the square root of 2 starting at 1, there are solutions to Pell's equation. Oh, yeah, sorry. The question was, do the numerators and denominators count anything? They're the solutions to Pell's equation in the case of root 2 starting at 1. And that was the perspective I had coming into it, was I knew that when you look at the continued fraction for square root of 2, you got interesting numbers out of it.
I had a question out of curiosity. That example is 40 billion digits similarity. Do we know which actually, what is the first position, first digit where they're different?
Yes.
No.
So the question is, with the 40 billion digits of accuracy to pi, do you know the first digit where it differs? You can write down very precisely. If you take the Jacobi theta transformation, So if I go back to that slide. Very good. There we go. So if you take the Jacobi Taylor transformation of that, the transform of it is something like the inner exponential is e to the minus pi n squared times 10 to the 10 instead of divided by 10 to the 10. And so you have the first term, you get an extra pi floating around from the transformation. And then the first term is 1, and then the next two terms are the same magnitude, and they are e to the minus pi times 10 to the 10. And so that is the place where it differs, and by exactly how much. And the next place it differs is e to the minus 4 times pi times 10 to the 10. And so you know the next difference as well. So you have extraordinary accuracy in terms of knowing where it, how much it changes, how much it differs from. In fact, I posted this to Facebook on Pi Day this year, and a number of people wrote in comments, oh yes, that's easy. This looks like a normal integral. So you do the obvious approximation and it gives you that about just, this is what it should look like. And they get a reasonable approximation of the first area, but they don't get anything like the second term and the fourth term.
More questions for Neil?
Anybody uses this to actually compute?
No. No, it's an intellectual curiosity. There's a wonderful book called the Pi Source Book. Not this thick. It's a collection of reprints of papers about pi. It doesn't have the one that proves it, but it does have this in it. And I was actually teaching a class on mathematical history on Pi Day 5 or 6 years ago. And I looked up to find a precise statement of a theorem, Borway, Borwin, and Filcher about Gregory's series for pi. And on my tablet, on the same page as the this error term for Gregory's series, right above it was this. And so I walked back to my office from the classroom going, okay, exactly what type of transformation do I need for this? I figured out enough about how to prove it that by the time I got back to my office, I looked up the correct transformation and wrote down the proof. So it is very easy to do, but people don't look at it that way.
Let me see if there are questions online. So, okay, let's thank again Neil for wonderful talk.